So last time we have started to talk about end behavior of functions. That is to say, what is the function's tendency as x is very large positive and as x is a very large negative number. That is the same as visually, what is the function going to do after it left the depicted part? The problem with our graphs is that it's finite and we're trying to depict something infinite. The end behavior of functions is a limit of f of x as x approaches negative infinity. That's the left end behavior of the function, and the right end behavior would be the limit of f of x as x approaches positive infinity. All right. We never rigorously defined limits. Then we looked at the end behavior of basic functions. Just by nature of understanding them, we stated their end behavior, and then we sort of started to look at trickier end behaviors, and we ran into a list of properties that are sort of intuitive. These are actually the properties of limits that were mathematically proven from the mathematical rigorous definition of the limit. So we don't have this definition, so we're not going to have these proofs. The nice thing about these laws that they are kind of intuitive. For example, the sum rule states that if we add a function f plus g, as x approaches infinity, that function has a limit, and it's the limit of f of x and g of x in the sum. We did not rigorously prove that, but intuitively the question would be, what happens when we add a number really, really close to 3 to another number extremely close to 10? And our instinct would say that it would be pretty close to 13. So that limits behave nicely with respect to addition. If you look at this list of properties, it's basically we're performing the operations that we would want to do to numbers. Okay, so we found that these operations were as we expected, as long as the limits were fixed numbers like 3 and 10. Things became a little bit stickier when one of the functions did not go to a number but to infinity. But that was okay too. For example, we could say if we add a number that's really, really close to 3 to another number that is insanely large, I think we all have the instinct that that's still going to be pretty big. Things became interesting when both f and g had end behavior that were infinity. For example, so I think we all have the conviction that this should be infinity because we're adding a gigantic number to another humongous number. So of course the answer is going to be very, very large. So the answer here is infinity. So we could handle that using our intuition. But what if we subtract them? All we know is that we're subtracting a very large positive number from an outrageously large positive number. Well, which one is bigger, right? So this is a case of indeterminates. Think of indeterminates that there are two gigantic but opposing forces. There is no problem when they're sort of helping each other, right? But once they start opposing each other, then we have no idea which one is stronger. So here is the thing with indeterminates. First we have to recognize it. Then we have to stop using our intuition. Instead, we have to bring that expression to a form in which it is no longer an indeterminate. So all kinds of algebraic transformations will come up. A lot of tricks could come up here. And so we bring it to a form where it is no longer an indeterminate, and then we're using our intuition to figure out the limit. Now, when I say we use our intuition, that is the same as using that list of properties of limits. A few times I'm actually going to prove even the intuitive part too, just to show you that it's the same thing as using those properties of limits. Okay, so we have seen indeterminates last time, but very simple ones. So this is an infinity minus infinity type of an indeterminate, right? Because this is a very large positive number, and this is a very large positive number as x approaches infinity. And we're subtracting one large number from another one. our intuition shouldn't, because sometimes yeah, the first number is bigger, but ever so slightly bigger, that in the end result it won't matter. So we have infinity minus infinity. We need to stop with the guesses and manipulate this algebraically. And this one is quite easy, because what's going on, if you recall, 5 to the power of x plus 2 is the same as 5 to the x times 5 to the 2 by the very first rule of exponents, and so it's 25 times 5 to the x. And now this is 25 of them minus 1 of them. That's how many times we have 5 to the x power. So 25 minus 1, that's 24. To go rigorously, we would use the constant multiplier rule and say that this limit is the same as 24 times. So that's the constant multiple rule in limits. And now this here approaches infinity. We multiply it by 24, that's even more. So the answer is infinity. So last time we have seen other examples, so I'm not going to repeat all of them today. Okay. This is not an indeterminate, right? We divide 1 by a humongously large positive number. The answer is 0. This thing is going to get smaller and smaller, which is the same as approaching 0. Now what about this one? Here, as x approaches negative infinity, so now we are instructed to think of x as an outrageously large negative number. And then inside we have negative 2 divided by x to the 5th power. So it doesn't matter whether we are at infinity or negative infinity. In both cases, it's a very, very large number, and when we raise it to the 5th power, that is even larger. And now that we put it in the denominator, it's going to be a very, very small number. After we multiplied it by negative 2, it is still a very, very, very small number. So this here is 0 as well. In general, as x approaches infinity, a constant number divided by any power of x, as in all such cases x, therefore x to the nth are humongous numbers, therefore when we put that in the denominator, that will result in a limit of 0. It's not that this one is so difficult, but as it turns out, we're going to use this a lot. So this is one that's very useful for us. Okay, so this is going to be our first indeterminate that is new. These terms, if you ignore this negative sign, both approach infinity, right? And then we subtract. So the question is who wins out here, if anyone? Maybe there is a balance. This is an infinity minus infinity type of an indeterminate. I'm going to show you two things, how to think about it, and then I will also show you how to prove it, because the two are different. Here is how you can sort of get the idea intuitively. What's common between them? X to the 7th, right? Now, what are they getting multiplied by? This x to the 7th is getting multiplied by 10,000, and this by 2x. So who's going to be bigger here? And so basically, we compare 2x with the 10,000. And this is kind of the art of being sloppy, that you're going to realize that it doesn't matter how big a number is. If it's fixed, then x approaches infinity will always beat it. And then we develop this tone like, oh, this is finite. This is just finite. And this isn't. So on the long run, the higher degree piece will become much more significant than the rest. But that's not how we prove it. This is how we think about it. Let me show you how to prove it, and full disclosure, there are many different ways. And I hope I'm going to show you the one that's on my handouts. Okay. So our intuitive idea is that they are both big, but this is so much bigger that compared to this becomes insignificant. Well, in that case, we should be able to show that it's insignificant instead of just arguing for it. So one way to do that, again, several different ways. So one way to do that is to factor out the entire leading term as it is, the whole term. So then we get 2x to the 8, 2x to the 8, we have the limit, sorry. And then here, now we intentionally factored out too much, right? Because the leading term is the highest degree, so everyone will be deficient. So we're going to get things like 5,000 divided by x. If you're not sure, the multiplication backwards should work. And now, okay, so what rule did we use here? This looks like the product rule of limits. And then, well, let's just leave this alone. Let's worry about this. Because even though algebraically this looks intimidating, this is a very friendly factor here, right? And as I said, we're going to use this rule a lot. That's how we prove that something is insignificant compared to something else. So x is gigantic, 5,000 over x is tiny, approaching 0, and that small number is being subtracted from 1. So as long as we factor out the entire leading term, this limit will always be just 1. And so we don't even have to worry what this limit is, because you see this is a multiplier of 1. So whatever this term wants the limit to be, that is what the limit is going to be, right? So we literally prove that the limit of this is the limit of the first term. So the second term has no saying in what the limit is. And by the way, that limit is infinity, right? This approach is infinity. Okay. So one can easily prove this for longer polynomials. If we factor out the leading term in a polynomial, then we're going to get limit as x approaches infinity, that leading term times something that approaches 1. So real fast, I'm not going to do the entire computation. Notice that I'm presenting these polynomials in organized by degrees, that may not be the case. So if you find a polynomial that is not arranged, just rearrange it automatically. Otherwise, you can make all kinds of mistakes about the limit. And so what we're going to do is we're going to factor out the entire leading term, and then this other factor, which will have 4 pieces. The first will be of 1, and the rest will have x in the denominator, therefore will approach 0. So you can say the limit of this product is the product of the limit of this and the limit of that. And the limit of this ugly long thing is just 1. So 1 is a very polite factor in case of a multiplication. It's whatever the other guys want. So in this case, the leading term determines the end behavior. So we have just not proven but made a really convincing case that the end behavior of polynomials is entirely determined by its leading term. And you're required to be able to prove it using limits instead of just stating this fact that we found. I'm actually tempted to look at rationals at this point. Okay. So here is what we're going to do. We're going to do the same thing that we did to polynomials upstairs and downstairs. So we're going to factor out the entire leading term in both numerator and denominator. And then 2 things will happen. First of all, these ugly things will be completely insignificant, and this whole thing is approaching 1, right? Which means that the entire end behavior can be determined by what this is. Oh, we forgot to establish this is an infinity over infinity type of an indeterminate, right? That's another thing that we don't know. A huge number divided by another huge number. Well, which one is bigger? So these two can be consolidated into a simple single expression, and that expression could be, and now there are a few cases. Sometimes you can have more in the numerator. Then, for all practical purposes, the expression will behave like a polynomial. Or they can cancel out altogether, and then you're going to have a number as end behavior at both ends, which is a horizontal asymptote. Or we can have more downstairs, which is our example right now, which means the whole thing will behave like, surprise, we're using it again. It's like 1 over x to the n as x approaches infinity. So here we could get either a polynomial or a number, or run out of all the x in the numerator and have x left in the denominator. Well, right now this quotient is negative 3 over x. And then the end behavior is going to be 0 at both ends. let's perform the computation, which is not difficult, maybe tedious. The multiplication backwards should work. Now we're going to apply the product rule of limits, which says that if you have this piece and this piece multiplied, then if both limits exist, then the limit of the product is the product of the limits. So we can take the limit of this, the limit of that, and multiply. And so here we can simplify. And this piece is a lot of writing, but not much thinking. And this whole thing approaches 1. And then negative 3 over x, the limit will be 0. But if you're varying positive or negative, it will follow. So whether it's small positive or small negative, it will behave exactly like negative 3 over x is. So that is about end behavior of rational functions. You're going to see probably a lot of these. This is the smallest, cutest little rational function in which both numerator and denominator are linear. And again, if we just apply the same technique, namely factor out the leading term, it's going to do the trick. So we factor out 3x from the numerator and x from the denominator, right? And now x cancels out, so what we have is the limit as x approaches infinity, 3 times limit. Now we can write the limit of this product as the product of the two limits, right? Even on the sheet that's restricted to finite, this is a finite number really close to 3, and this is really close to 1. Now how can we say that this is 3? That is the constant rule that I believe is the first rule on this sheet of properties of, the first rule that says that the limit of c is c. Okay, so on quizzes, exams, I want this computation. Don't just cross out the x. I actually want you to be able to prove it, to verify it using this computation. Okay, next up. Also check out the indeterminates at the end of the previous lecture. Okay, so this is our next example. Now let's see. If x is a large number, then 1 over x is nearly 0. So 1 over x is kind of insignificant. So the top is really very, very close to 3 minus square root of 9. That's 3 minus 3, that's 0. And the bottom is very, very close to 0 as well. So what we have now is a 0 divided by 0 type of an indeterminate, which means the problem is not over. The answer is not that this limit doesn't exist. The answer is still far, because first we're going to have to manipulate this expression until it is no longer an indeterminate. Well, that's the bad news. The good news is when you see radicals, think conjugate, and most of the time that will do the trick. So we see a radical, so let's use its conjugate. Our first step is going to be to multiply this expression by 1, where both numerator and denominator are going to be the same thing, the conjugate of the expression with the radical in it. For the second line, don't worry about distributing it where it is not two conjugates. So in the denominator, we're just going to indicate this multiplication. And now let's see what happens when we multiply these two conjugates. So 3 times 3 is 9, and then 3 times the radical, and minus the radical times the 3. Those two cancel out each other. Hence the difference of squares theorem. So we get 3 squared minus the radical squared. So that's 9 minus 9 plus 1 over x. And be careful, there is an error on the paper right now. We are subtracting this entire thing. The radical is no longer there to suggest the parentheses, so we have to put it there ourselves, and this is still a limit. Okay, so now when we subtract, 9 disappears, and now there is one more cancellation, and what we have is it cannot be an indeterminate anymore because the numerator is negative 1. Now as x approaches infinity, 1 over x gets closer and closer to 0, so this sum gets closer and closer to 9, whose square root is getting closer and closer to 3. So the answer is minus 1 over 6. Now that is not a limit we can find using our intuition, right? This was the question. Negative 1 over 6 is the answer. That's a really good illustration that even that our intuition has its limitations. So maybe we could. Now, one more thing, and I promised to do this one. So here is limit as x approaches infinity of -1 over 3 plus square root of 9 plus 1 over x. Okay. So here I would just repeat myself. 1 over x really small, add to 9, now it's close to 9, square root of it close to 3, 3 plus 3 is... So, we're gonna actually prove this using those limit properties. I don't find this particularly interesting, but I think you should be able to do this when prompted. So, if we look at the list of properties, first we're gonna start with the quotient rule. This limit, if exists, is the same as the limit of the constant function -1 and the limit of 3 plus square root of 9 plus 1 over x. Right, we just took apart the top and the bottom using the quotient rule of limits. And then by the constant rule, this already equals to -1. Here, there's no space, so I'm going to move. So the numerator is already -1 by the constant rule. The denominator, we're going to say, we say that the limit of this sum is the sum of the limits. And then next, by the constant rule, the first number in the sum, the first term in the sum is a constant 3, and so the limit of the constant function 3 as x approaches infinity is 3. And now here we're going to apply the root rule, number 9, where we can say that the limit of the square root is the same as the square root of the limit. Now we're going to apply the sum rule, right? That under the radical, the limit of 9 plus 1 over x is the same as the limit of 9 plus the limit of 1 over x. And here we are. So when the expression is done being an indeterminate and we feel safe using our intuition, that intuition is broken down to this applying these properties that are very intuitive. So it's the same thing. So usually when it stops being an indeterminate, you can evaluate it. So I don't need you to write this all the time, but I wanted you to see it once. All right, let's see our next example. So this part goes to infinity. 1 over x squared is tiny. Add to half, almost half. 1 over half, that's the reciprocal of half, that's 2. 2 minus 2 is 0. So this is what we call an infinity times 0 type of an indeterminate. The question is, what happens when we multiply a gigantic number with a teensy tiny number? If you can think of a tiny number as 1 over a huge number, then basically it's a huge number divided by a huge number. So it's very easily can thought of as infinity over infinity. Well, we're multiplying a million by 1 over 100, or we're multiplying 100 by 1 over a million, right? Those will yield to very different results. Okay, in a way, this is the simplest type of an indeterminate, because all that we don't have radicals, logarithms, or exponentials like those examples, but we have an expression that is not simplified. So chances are, if you just simplify it, you're going to turn it into a form that is no longer an indeterminate. So just simplify it. So let's try that. So how is this not simplified? Well, there is 1, 2, 3 fraction bars, so that's never good. One is enough. As long as it has more than one fraction bar, it's called a complex fraction, and it can be simplified. So first, we're going to bring stuff to the common denominator inside. 1 over 2 plus 1 over x squared. The common denominator is the product, 2x squared. And then we're going to have x squared plus 2 in the numerator, right? Now that's this. I'll just write it down, since I'm going to make you write it down too. Now the fact that this is a bigger division sign, that actually matters. we would get completely different answers if we modeled up the order. We divide this, and then 1 is being divided by that. And to divide is to multiply by the reciprocal, so we end up multiplying 1 by 2x squared divided by x squared plus 2. Okay, it's still not really simplified, because we could, even though there is just one fraction bar, we have simplified this, but I think we would be better off if we could have a product upstairs and downstairs. Let's just bring stuff to the common denominator, which is then x squared plus 2. And so 2 is 2 times x squared plus 2, right? Because when we cancel out, we get back that 2 minus 2x squared. I don't know if you see that where we're going, but we're approaching a rational function. We already have seen how to compute those rational function indeterminates. So we have x squared times, the denominator is x squared plus 2, and in the numerator we have 2x squared plus 4 minus 2x squared. The 2x squared will cancel out. 2x squared plus 4 minus 2x squared cancels out. And now what we have, 4x squared, write this x squared finally, divided by x squared plus 2. And now we have a fairly simple rational function, so we're going to factor out the leading term, both numerator and denominator. So then 4x squared, there's nothing to factor out in the numerator, so we factor out x squared, and then we get 1 plus 2 over x squared. So what is that limit? X squared will cancel out, this thing goes to 1, so we have 4 divided by 1, which is 4. That's not so obvious from here. Not just that the limit would be 4, but even that it exists. I think it's a fine balance, and you may notice that we had x squared here, x squared here. If you change one of the numbers, then this balance, this fine balance, will be broken one way or the other. So we could have all kinds of outcomes here. So we have an infinity minus infinity type of an indeterminate here. Right, both p's approach infinity as x approaches infinity. So because we see radicals, let's try with the conjugates. So even though this is not a fraction, we're going to make it so, just growing on. And we're going to multiply both upstairs and downstairs by the conjugate of the radical expression we have. So it's x plus 5 under the square root plus root x. So we get limit as x approaches infinity. Now, what do we have in the numerator? The denominator is trivial because 1 times anything is just that anything. But what's in the numerator? We get the difference of squares theorem, this squared minus that squared. The other stuff cancel out each other. So we have x plus 5 minus x. And so we have 5 over square root of x plus 5 plus square root of x. Now is this an indeterminate? The answer is no, because we have a gigantic denominator and a very much finite numerator, which means that this limit is 0. So going back, we could say, well, I guess this difference wasn't significant enough. So let's see another one. See, again, we could speculate on what does this multiplication by 2 cause. But let's not do it. Notice the following. If x is billions and billions, then doubling matters, but this negative 5 doesn't. It doesn't matter. So what if it weren't there? Then we would be subtracting square root of 2x minus square root of x, which is the same as square root of 2 many square root of x minus 1 times square root of x. So it's root 2 minus 1 many square root of x. And that would approach infinity, right? This is just a finite number. 1.4141 minus 1 is a positive decimal, but this here will approach infinity. So our intuition that in this case tells us that the negative 5 can be ignored, then gives us infinity. And in this form, actually. So we can actually show that. And the process is very similar to with polynomials. So basically, we're going to factor out square root of 2x from here. Factor out the whole thing, so then there is going to be 1 and stuff that doesn't matter. So we have 2x times 1 minus 5 over 2x, right? We factored out the entire leading term under the radical. We can take the square root of a product, factor by factor, and so square root of x can be factored out. And then what's left is square root of 2 times 1 minus 5 over 2x minus 1. Right? So this thing goes to 1. And so we have the same expression, but instead of ignoring it, we just turned it into something that we know for sure approaches 0. So it's square root of x times square root of 2 minus 1. Now the only thing that matters here is whether this number is positive or negative. Because if this number is negative, the answer would be negative infinity, right? How much, how little, it's a fixed non-zero number, so it doesn't do much in a multiplication when the other factor approaches infinity. So the answer is plus infinity because this number is positive. Square root of 2 minus 1 is positive. Okay, that was fun. Thank you for watching.